So for this lesson, we're going to look at the extraction of aluminium. And to do this, we're going to have to build on our electrolysis theory. So the first part of the lesson, we're just going to quickly explore the process of extracting aluminium from its ore. Then we're going to look at the half equations, the ionic half equations that occur at each electrode during electrolysis. So let us look at a few basic uses of aluminium as pure metal or in its alloy state. So I'm just going to list down 3 uses and we're going to discuss them, and then you're going to give me 3 more uses, or as many as you can. So we can use them in pans. Okay, another one would be cooking foil. Okay, and I'm going to say, let's say aeroplanes. Right, I'll leave it there. So I've given you cooking pans, cooking foil, and aeroplanes. Now, I want you to feedback to me on Teams at least 3 more uses of aluminium or its alloy. And we're just going to discuss these 3 uses first, and then hopefully by the time we finish discussing these 3, you may have an idea of a few more examples. So here we've got cooking pans and cooking foil. Why would we be using aluminium in cooking foil and cooking pans, especially when we say that aluminium is quite reactive? Because if you look here you can see the reactivity series that we've looked at quite a number of times. Now I want you to focus your attention onto aluminium. You can see in terms of reactivity, it is quite far up the reactivity series. And yet we are using it in cooking foil and pans and cooking pans. So how could we be using aluminium for cooking foil and cooking pans if it's quite reactive? I'll give you a clue. It's something to do with the air. So it's something to do with the air that the aluminium is reacting with, and once it reacts with it, the aluminium becomes unreactive. I want you to think about this and type an answer back to me on Teams regarding what could the reaction be that occurred that rendered aluminium unreactive and allowed us to use it in these items here. So that's the first part. So aluminium becomes unreactive even though it's a very reactive metal, as you can see on the chart to the right. So based on its ability to become unreactive, what else could we potentially use aluminium in, or do we use aluminium in based on its unreactive property? Now, another point is, the third point here is aeroplanes. So aluminium is used, or its alloy is used in aeroplanes. What feature of aluminium is important or crucial for it to be used in aeroplanes, something that has to stay in the air? What feature would be important there? So something to do with helping an aircraft stay in flight longer, and this property is given by aluminium. What could it be? I'm not going to give you all the answers. I want you to think about it. I've given you 3 possible uses of aluminium. I want you now to feed back 3 more. and if you can, get a fourth one. And I want you to list them back to me on Teams. But in addition, I want an explanation as to why we are using aluminium in cooking pans and cooking foil. If you haven't managed to think of any uses, keep thinking, and when they come to you, hopefully before the end of the video, you should be able to get a few down and get an answer back to me. Alright, okay, so here are some few points that may help with your answers. Aluminium alloys have a low density. So, low density, but having said that, the alloys of aluminium or aluminium alloys are very strong. Okay, low density, very strong. They also form an oxide layer. This oxide layer is easily formed and it naturally forms for aluminium. So these 3 bullet points should help you if you struggled with the previous section. Okay, so let's move on now. So aluminium is quite reactive, as we can see from its position on the reactivity series. Now, it's less reactive than magnesium, so it's below magnesium, but it's more reactive than zinc and iron. And where does that leave us? That leaves us just above carbon. Now this is important because carbon cannot be used now to extract aluminium, whereas carbon could be used to extract the metals below it, but carbon cannot be used here to extract aluminium. So can we just put down carbon cannot be used to extract aluminium. Okay, and why that is the case should be evident now by looking at its position in the reactivity series. Okay, so carbon cannot be used. Therefore we need to extract aluminium from its ore via electrolysis. Okay, so we cannot extract aluminium from its compounds. We cannot separate it from its compounds via carbon. So we need to perform electrolysis on the ore to separate it. Now, the compound that we are going to that electrolysis is going to be used for is aluminium oxide. So the compound from which we need to separate the aluminium from is aluminium oxide. But we need to go a step back. Aluminium oxide is mined from the ground from an ore called bauxite. We do not perform electrolysis on bauxite. Instead, we mine the raw metal ore, bauxite, from the ground, and then we purify it into aluminium oxide. So aluminium oxide is removed from the bauxite, and this aluminium oxide is broken down via electrolysis, and we separate out the pure aluminium metal. So let's put that into steps here. So carbon cannot be used to extract aluminium. Aluminium can we put down exists in its ore state, which is known as bauxite. It is this bauxite that is purified to aluminium oxide. So let's put that into an easier step to remember. Okay, so we have bauxite, which is the ore, which is mined from the ground. Okay, so bauxite ore. Okay, this is mined from the ground. We purify that and we get aluminium oxide. And then we perform electrolysis on aluminium oxide to get aluminium metal. So you can see the three-step process to get aluminium metal. And what I'll do is I'll just put, this is, we'll say, purification. Okay, and here we'll say electrolysis. Actually, let's put it, okay, purification from bauxite ore to aluminium oxide, and here we'll have electrolysis taking place to get our pure aluminium metal. Okay, so just be aware of where electrolysis is happening. Here you can see the bauxite ore where the aluminium oxide is being contained. So this is our bauxite. Okay, the bauxite ore. Now, the bauxite ore contains mostly aluminium oxide. However, it's mixed with other rocky impurities, and you can see that here. This does not look like the aluminium we are familiar with because there are many other impurities within that ore. And what you need to do first here is separate the aluminium oxide from the ore, from the bauxite ore that you're seeing. And the impurities that we're seeing mainly in the bauxite is iron 3 oxide. And that's why when you when you remove this, when you put this through a process of purification, you get the wastewater, which is brownish in color. And this also has to be stored in a separate, stored carefully in a separate place. So what we can do is we can just quickly note down that bauxite contains rocky impurities. Okay, so bauxite contains rocky impurities. Okay, and mainly, okay, can you put mostly iron 3 oxide. Okay, iron 3 oxide. And this is why we get this brownish color. And that's why we get waste solution. The waste solution from the separation process of aluminium oxide from bauxite gives us a brownish colored liquid to the brown wastewater, and this has to be stored. So results in brown wastewater forming after separation. from aluminium oxide. So separating out the aluminium oxide from the bauxite ore results in brown wastewater forming. Now you may be asked to talk about environmental impacts for extracting aluminium, and you could say this is something there. So here you can see aluminium oxide. This is after the purification process from bauxite. And here we have the aluminium oxide, and notice the chemical formula. So can you take the name down and the chemical formula of aluminium oxide? Because this is the chemical, you're going to need to know that when we come to balance equations. Now, when we now take this aluminium oxide and try and get pure aluminium metal from it, we need to first melt this aluminium oxide if we're going to actually use it in electrolysis. Why? Because in electrolysis we need to have ions that are moving, that are free to move. Now, to make electrolysis happen with aluminium oxide, generally on its own you will need a lot of energy. And the reason that we need a lot of energy is because we need to melt the aluminium oxide. And to melt aluminium oxide, you need a temperature of approximately 250 degrees Celsius. And this makes it very expensive then, because your energy costs are going to be higher. Now, what we do is, to lower these costs, we mix the aluminium oxide with another substance which is called cryolite, and the cryolite is also in a molten state. So cryolite is an ionic compound which is made molten and mixed with aluminium oxide. Now, this mixture allows electrolysis to happen at 850 degrees. So we reduce the temperature required for electrolysis to happen to 850 degrees. So we've reduced the temperature from 2050 degrees Celsius to 850 degrees Celsius by the addition of cryolite. So by adding cryolite, we reduce the temperature from 2050 degrees to 850 degrees Celsius. And this allows electrolysis to happen at this temperature. Now, just a quick note, to get aluminium oxide, we do get an intermediate product first, which we treat to get aluminium oxide. So what happens is that we have our bauxite, our ore, our aluminium ore. Now, in the purification process, so when we purify aluminium ore, the bauxite ore, we first get a product known as aluminium hydroxide. So what happens is that we've got bauxite ore undergoes a purification step. Now, when we purify aluminium oxide from the ore, we get aluminium hydroxide. So this is going to give us aluminium hydroxide. This happens in the purification step. So the purification of aluminium oxide from the ore makes aluminium hydroxide. Now, this is separated from the impurities, from the bauxite impurities. But to get aluminium oxide, we need to heat this aluminium hydroxide, and by heating aluminium hydroxide, we get aluminium oxide. So this is the process, the purification process to get aluminium oxide. Let me just put that. Okay, so just be aware, to go from bauxite to aluminium oxide, it's not a simple case of filtration. You have to separate the impurities out to get, and by doing this, by this process, we get aluminium hydroxide, and that is heated, and that gives us aluminium oxide. And this is turned back to pure aluminium oxide. So let's put some summary key points for the extraction of aluminium from the ore. So first point is that aluminium oxide has a high melting point of 2050 degrees. Okay, so Al2O3 has high melting point of 2050 degrees. Let's say approximately this value. Cryolite, molten cryolite, okay, which is an ionic compound, okay, molten cryolite, which is an ionic compound, is added or mixed with the aluminium oxide. So molten cryolite mixed with Al2O3. This results in a lower melting point of 850 degrees, and now electrolysis can take place, because once we have the Al2O3, the aluminium oxide, in a molten state, electrolysis can take place. So in essence, I'll repeat again, the aluminium oxide is mixed with molten cryolite to lower its melting point, reducing the energy needed to extract the aluminium. So if we go from this temperature to this temperature, this means that we have less energy costs. The overall reaction for the electrolysis of aluminium oxide is as follows. Aluminium oxide, I'm going to give you the word equation here. Aluminium oxide, and if we put electrolysis here, once it undergoes electrolysis, we get aluminium plus oxygen. Okay, so that's our word equation. I'm going to give you a partially complete equation, which I want you to fully balance and complete. So I'll give you the oxide, okay, and what we get is aluminium plus oxygen. Now I want you to complete this equation as fully as possible, balance it and complete the equation. So if there's anything else that needs to be included for a complete chemical equation, what else needs to be there, and I want you to include it. So balance it and complete this equation fully. So just pause the video here and balance and complete this equation. Okay, so you should have 2 here, 4Al and 3O2. But we're not finished because we don't have any state symbols. So to complete this equation, we needed the state symbols, and you must have aluminium oxide in a molten state. So if you had put aluminium oxide as a solid state, you would have lost the mark because it must be in a liquid state, molten state for electrolysis to occur. And aluminium here again must be in a liquid state because we're still in an electrolysis cell. So the aluminium pure metal is still in its liquid state, and oxygen should be a gas. So this should be the equation that you have. So can you ensure that you take down this equation, that you have this equation fully in your books, in your notebooks? We're going to now look at specifically what is happening at each electrode. So we have a negative electrode and a positive electrode. On Teams now, I want you to type back to me what we call the negative electrode. So I want the name of the negative electrode. Okay, so on Teams, I want you to type back the name of the negative electrode. Then I want you to type back the positive electrode. Okay, so type back the names of each electrode, what we call them on Teams now, please. So pause the video here and type back the answer to me. Now, when we look at each electrode in detail, we have to also specify where what product is being formed at each electrode. So what we say is that aluminium forms at the negative electrode. Okay, so just make a note of that, underline negative. Aluminium is forming at the negative electrode. Oxygen is produced at the positive electrode. Okay, and just underline positive electrode there. Now, when we look at the oxygen in a bit more detail, we need to understand that it's going to react with carbon, which is the electrode, which is the positive electrode. And when it reacts with the hot carbon positive electrodes, we get carbon dioxide gas being produced. So if we look, let's put it in this color. Okay, so the oxygen is produced at the positive electrode. Now, the positive electrodes are made of hot carbon, and this results in carbon dioxide gas being produced at the positive electrode. So we get this reaction, carbon in a solid state, which is the positive electrode, reacts with the oxygen that's being formed there, and what we get is carbon dioxide gas. What you can see here is a diagram showing you a cell used in the extraction of aluminium by electrolysis. I want you to take down this diagram into your notes as well. So you need a copy of this diagram somewhere in your notes, so you're fully aware of where the positive electrodes are located and where the negative electrodes are located, where you're getting aluminium building up, how the aluminium is taken out of the cell, and you also need to be focusing your attention at the carbon dioxide gas being emitted from the positive electrodes. What I want you to do is, once you've taken down this diagram in your notes, I want you to answer this question in green back on Teams. The carbon positive electrode needs to be replaced. Why? So take a look at that diagram, look at your notes, and I want you to tell me, why do we need to replace the carbon positive electrodes in this cell here? Here you have two half equations for the electrolysis of aluminium oxide. I want you first of all to copy down these two half equations and note them down as being half equations. Then I want you to type back an answer. Once you've written the answer down yourself, I want you to type back an answer explaining each half equation in terms of oxidation and reduction. So decide which one's being oxidized and which one's being reduced. Then I want you to use those two keywords correctly along with the keyword electron, and give me a sentence or two for each half equation. So you're going to take the first equation for aluminium, then you're going to tell me, has it been oxidized or reduced in terms of electrons, and you're going to construct an answer. Then you're going to do the same thing for oxygen, and I would like both answers typed back to me on Teams.